Hello, everyone, and welcome to today's webinar. My name is Celeste Rupp, and I will be your moderator for today. This webinar is brought to you by the Critical Materials Innovation Hub, and our presenter today, Hongyue Jin, is going to talk to us about how to conduct techno-economic analysis and lifecycle assessment. Before we dive in, I want to go over a few webinar logistics for you. First, this webinar is going to be recorded, so please oh my goodness, my brain just escaped me. I'm so sorry. This webinar is recorded, and the recording will be available to you all in about a week's time, posted on aimslab.gov/CMI and also on our YouTube channel, Critical Materials Innovation Hub. During this presentation, I encourage you to please ask questions. Ask those questions using the chat feature of Teams. Hongyue will address those at the end of her presentation today. If you have suggestions for future webinars, please let us know. You'll receive an exit survey following today's webinar, and you can also email us at cmi@minds.edu. And with that, I would like to introduce you to our presenter today. So we have Hongyue Jin. Hongyue Jin is an associate professor at the University of Arizona, where she is focusing on techno-economic analysis and life cycle assessment. She is also the CMI's cross-cutting research focus area deputy. So we are excited to have Hongyue with us today and excited to learn from her. And so with that, I will pass it off to Hongyue.
Thank you, Celeste, for your nice presentation. Hello, everyone. It's my pleasure to talk with you about how to conduct techno-economic analysis and life cycle assessment. As the start, I would like to introduce you about briefly what is techno-economic analysis, abbreviated as TEA, as well as life cycle assessment, abbreviated as LCA. So TEA is a method to evaluate the economic performance of a technology. Recently, or about 2 years ago, DOE had a series of introduction and webinars on how to conduct TEA and LCA. In there, it was defined as TEA to assess the overall economic value of technologies and allowing analysts to objectively weigh benefits against cost, and that it can be used for evaluation of pre-commercial technologies. And sometimes we get the question of, does TEA means techno-economic analysis or techno-economic assessment? I would say they are exactly the same, and I will use them exactly the same meaning in TEA. And particularly in this webinar, I would like to talk about using some lab or pilot scale experimental data to project the industrial scale operation, which is a widely used application of TEA. Next. Okay, LCA is a standardized methodology, so it's more standardized than TEA, according to International Standard Organization and other organizations that have made significant effort in standardizing LCA methodologies to assess the environmental aspect of potential impacts associated with product, process, and services. This is a definition according to the U.S. Environmental Protection Agency, EPA. And again, life cycle analysis is the same as life cycle assessment and LCA. I'm going to use them all the same thing. LCA is traditionally more retrospective, so it's looking at past data. So we call it ex post LCA, but emerging efforts have been looking at the prospective LCA, that's looking at new technologies, new products, new processes, what will be the impact to the environment when we introduce them to the market in a large scale, and we call it ex ante LCA. So this talk will be more focusing on the emerging, prospective, anticipatory ex ante LCA. Okay, why do we want to conduct TEA and LCA together? There are some synergy in data collection and modeling efforts between this TEA LCA, which you can see throughout the webinar today. So we can reduce the efforts of conducting the analysis, but benefit with more comprehensive understanding, especially the trade-offs of economic and environmental impacts, so that we can minimize the effort, maximizing the synergy and benefits. Okay, there are two broad types approaches of conducting TEA. One is top-down approach, such as using historical data from similar projects to estimate cost, revenue, and other data for the current project. And this is especially useful when we are in the very early stage of estimation process where the alternatives are still being developed and refined, so we don't have much data. So one excellent example is the last month's CMI webinar where Dr. Tim O'Brien from USGS talked about how to estimate mining project cost to model the future mineral supplies and costs. So this is collecting a lot of data to give a reference and then developing some models to help us to estimate new project cost, revenues, and other information based on prior data and modeling. Today's talk will focus more on the bottom-up approach, where we break down the entire project into smaller unit process level and estimate the economic consequences of each unit process and add them up. So we start from bottom, very detailed specific process data, and add them up to move up. So this will be a bottom-up approach. It's helpful when we have more details available, such as technological detail, process detail, so we can use it to estimate the cost, revenues, and other information. Similarly, LCA has the two approaches or three approaches that is in a similar realm of top-down and bottom-up. So top-down approach, I can think of economic input-output LCA, where we start with the economy-wide, very comprehensive impact. Let's say the United States, the total carbon footprint we emit per year, and then divide them by the sector-wise, such as agriculture, maybe electronics, manufacturing. And then we dive deeper into the different product categories, and we use more average data, publicly available information, and it is much faster and cost-effective. In today's talk, I'm going to focus on the bottom-up approach, which is process-based attributional LCA, which is very detailed process technology specific analysis so that we can make tailored analysis and suggest improvement opportunities. It is time consuming, it is costly, and often involves proprietary data. And one example that can differentiate the economic input-output LCA and process-based LCA, attributional LCA, is the iPhone versus Android phone. So in economic input-output LCA, we cannot differentiate the impact of these two products because they are all under the same category of phone, hence cell phone. It doesn't differentiate particular product, particular technology, so it's very high level. As opposed to the process-based attributional LCA, we'll look into how do we make those phones and how do we transport to the final customers and how it was used. So it's very comprehensive, it's a very detailed and product or technology specific. And as opposed to, there is another approach called consequential LCA, which is using the process-based attributional LCA added with the market impact modeling. So coming back to the iPhone versus Android example, so if one decide to think that iPhone was too expensive, so they want to buy the Android phone as a cheaper alternative, then attributional LCA tend to think one-to-one substitution, so that one iPhone is substitutable to one Android phone. But for consequential LCA is looking at the impact beyond this one-to-one substitution. So if I buy Android phone, I can save money and I use that money to buy something else. So let's say Arizona is currently very hot. Since I saved that money, I use that money to turn on the AC to a lower temperature. So I spend that money used for AC electricity. So that will have another environmental impact. So consequential LCA is modeling the additional market or indirect effect. And it's looking at the marginal data, such as my behavior of changing from iPhone to Android, etc. It is time-consuming, costly, involve proprietary data, and in addition, it will have economic modeling, which makes it more uncertain. Okay, coming back, I'm going to focus on process-based LCA in this talk. Okay, as an example, I would like to show TEA-LCA applied to acid-free dissolution recycling, ADR, of rare earth elements, REEs. So this technology was developed by Ames National Lab. The researchers are shown in the photo, Dr. Aikina Nelbiden from Ames National Lab and Dr. Dennis Produce from Ames National Lab. And the key innovation is to use copper salt, initially it was copper nitrate, to selectively dissolve rare earth elements from a variety of feedstocks. So in this particular example, I'm looking at magnet swarf. About up to 73% of rare earth permanent magnet, in particular NdFeB magnet production, are wasted as a magnet swarf, manufacturing waste during the machining process, like grinding and shaping. And this magnet swarf contains a lot of rare earth elements, approximately 30%, and they can be subject to this acid-free dissolution recycling process to produce rare earth oxide. And this technology has been licensed to Critical Materials Recycling, CMR, and Mr. Dan Bina's photo is shown here from CMR. And then the TEA-LCA was conducted in collaboration with this team, as well as Purdue University and then University of Arizona. And this TEA-LCA was conducted at an early stage of technology development at the TRL level of 3 to 4. TRL is important because when we have different TRLs, we tend to try to answer different questions according to our TEA-LCA. So with the lower TRL level, we want to have some screening or order of magnitude estimate. As the technology is still under development with a lot of uncertainties and moving parts, the goal is to have a general understanding of whether the technology will have a commercial potential. Does the technology provide more value than existing products? And then we want to prioritize future research direction. So according to this initial TEA-LCA, we can identify what are the bottlenecks, what would be the best parameters that we want to optimize through further R&D to improve the technology. Those are the questions and goals for the early stage TRL level TEA-LCA goals. As opposed to for higher level TRL, we want to have more definite or detailed estimate. Then we will want to know more or less exact cost and revenue, and whether we should invest to build a facility, whether we need to expand the facility, how should we value of the project, so that we can negotiate how much equity we need to give away for how much of a cash investment. So kind of valuation decision, investment decision, more of a strategy. Okay, other goals of TELCA. In this talk, I'm going to focus on the low TRL TELCA. And in this case, we first want to quantify what is the potential economic and environmental impacts. As the old saying says, if we can't measure it, we cannot manage it. Especially for environmental impacts, it's not tangible. We don't pay cash. It's difficult, and we want to first measure it. And then we identify what is the cost drivers and what are the environmental hotspots. What is the bottleneck that we want to improve the technology further? Which aspect of the technology we want to invest to improve for improvement? And those improvements based on the bottleneck could be material choice, process efficiency improvement, product design, many different aspects. And then we want to compare the technology with the alternatives and see what are the advantages and disadvantages. And I would like to mention that TEA LCA, especially on early stage TRL, is iterative process. We want to go over this process from 1 to 3 or 1 to 4 iteratively to continuously improve the technology. And finally, it can help inform decision making, such as supply chain configuration, priority setting, or policy setting information. Okay, the scale. Both TE and LCA, we want to model industrial scale operation. There is less meaning in estimating what would be the cost or environmental impact of doing lab scale experiments. In our prior example, this is 50 grams of swarf. We want to estimate the large scale adoption impact. So that in our previous example, we looked into 100 tons of swarf per year recycling. And when we decide how much target do we need to set, we have at least two boundaries. One is the feedstock availability or chemical reagent material energy availability and demand for the final product. And we need to have a minimum, at least a minimum of these parameters to set our target production of critical materials or anything. And then the TEA result may be normalized in, for example, dollar per kilogram of rare earth oxide. However, for attributional LCA, process-based LCA will almost always normalize the results according to something called functional unit. Functional unit is a quantified performance of product system for use as a reference unit. Let me show you an example. Why functional unit is important? I'm showing two examples. The first example functional unit is 1 metric tons of e-waste recycled. Is it a good functional unit? It has a number, target like metric, 1 metric tons. It has the product, e-waste, being recycled. Example 2 is 1 kilogram of 99.5% or higher purity mixed rare earth elements recycled from e-waste. It's more specific. It's from the angle of output product. So the goal of our project is to recycle rare earth elements from the e-waste. By showing example 2, the purity, output form, and the number, it will help readers to understand the efficiency of the product and the function of the product recycled into rare earth elements. So example 2 is better. When we review LCA literature, both examples show up, and I think the example 2 is better, especially if the major function of the activity is to this recycle rare earth elements. And it's crucial for comparison of different technology. For example, example 1 doesn't show the process efficiency. Some technologies may take 1 metric tons of e-waste to recycle 20 kilograms of rare earth. Other technology may recycle the same amount of e-waste but recover double of that rare earth. then the first example does not show difference in the technology performance. Okay, data collection and modeling is a crucial step in TE and LCA because garbage in, garbage out. How can we manage the quality of the data in that will make the output more reasonable, accurate? So there are four key components into this data collection and modeling. The first one is mass and energy, which I think is the often most time consuming and challenging part that we want to track all the input and output, mass and energy, amount, as well as cost and impacts. And the second one is equipment, other capital. And then labor. Labor is only for TEA. In LCA methodology, labor is excluded, assuming the impact of labor is not affected. I mean, the person work on this particular technology or not, the person's environmental impact is assumed to be not different. So labor is not included in LCA, and other costs that I will talk about are only pertinent to TEA. Okay, the mass calculation, we first start from the process flow diagram, and we want to bound our scope, system boundary. Which process, where do we want to start the process and where do we want to end the process? And this figure on the right shows the example from the ADR technology I mentioned before. So it shows using a dash box to show the boundary of the analysis, and it shows the processing steps. Each processing steps are called unit operation, the smallest possible processing step that we model, and then we add all the impacts together to derive the total impact. So this is a bottom-up approach. And then we estimate material inputs and outputs. So the feedstock, how much do we need? And then whether there are some chemicals. In this case, we use copper nitrate and water and ammonium hydroxide. Don't forget to include the waste. We want to track the waste as well. And we always want to verify the quality of the data. One easy comparison that is common across many projects is measure the difference between the experimental data and the stoichiometric calculation from the chemical reaction equation. If everything goes well, what is the minimum amount of each material we need so that we can have some check in the data quality and know how much is potentially improvable if the technology advances. And then we want to define the mass as a function of processing condition. So this is called parametric modeling, parametric TEA, parametric LCA. So one example is solid to liquid ratio. Is there some equation that can link the amount of this copper nitrate required according to the initial feedstock amount? So solid, copper nitrate solution, this will be liquid, and then the solid is the swarf. So when we receive different information from different experimental data, we can easily update the parameter to automatically update the TELCA results. So this will enable process optimization. And there are some software, simulation software available that we can purchase. Some are free to simulate the process and help us make this mass estimation more easily, such as Aspen, SuperPro Designer, MassSim. And some of the processes do not allow parametric modeling, and some of the processes may seem to be more of a black box or more easier user interface with the lack of transparency. So on the other spectrum is the Excel modeling, where you can see the raw data very easily and easily trace what's going on and embed those functions in the Excel spreadsheet. When the process is relatively simple, like the current example, Excel spreadsheet modeling was used. When the process is more complex, let's say hundreds of solvent extraction process, where you want to model which equipment goes first and how the materials flow in each equipment and the scheduling of different processes, then this simulation software will be very helpful. Okay, the next part is the energy estimation. Of course, if we can have some direct measurement from industrial process of the technology, it will be very helpful. It will be much more accurate. However, for new technologies that are not commercialized yet, we may not have this information often of the times. Then how do we estimate the energy consumption is a big challenge. And we cannot linearly scale the energy consumption based on lab scale equipment data. For example, when we centrifuge like 10 milliliter of liquid in a very small centrifugation lab equipment, it will be very different energy consumption in terms of dollar per liter of centrifuged liquid when we scale up to industrial scale. So there are some equations or methodologies out there that can help us calculate the energy consumption theoretically. Some example is shown on this table from this reference. And another approach is like proxy from similar process, like the one we mentioned before, the top-down approach of TEA, where we look into similar processes and see what is the energy consumption for those. And then equipment power rating. This will inevitably increase the energy amount calculation because equipment doesn't always run on the full power rating. So we want to compare different approaches of estimated energy consumption so that we know what is the bounds and uncertainties are to make a better assessment. Okay, and then we want to link the energy consumption with processing condition. Again, this will help us to optimize the process. By changing processing condition, we can automatically update the energy consumption so that we can iteratively work on reducing the energy consumption. In this process, we will need to know a lot of thermal physical properties. One website is shown here. It has my students use this website to get some properties such as vapor pressure, density, heat capacity, enthalpy, entropy, viscosity, thermal conductivity, heat evaporation, etc. And within CMI, we have several teams, several institution members who work on this, measuring these properties or predicting these properties in the cross-cutting research focus area. And then there are tools available like before, Aspen, SuperPro, MESSIM. They will use methodologies similar to the ones listed here to help us to get some estimated energy consumption. There is also this website that I found useful that can help us to design some equipment and estimate the energy consumption out of it. Okay. And then once we quantify the amount of mass and energy, how do we link it to the cost? Ideally, we want to use United States-based cost for United States-based TEA. If your audience from another country, you want to use the cost data from your own country or even better, your own location, because different locations have different cost. So these list data sources are mostly from US perspectives. Chem Analyst is very helpful. This is the number one to go for me to quote material cost. And then there are some others listed below. that you can explore. Most of them are free. And of course, if you pay to buy commercial databases, that's also feasible. The downside is that they don't always allow you to reveal the numbers, the raw data, so that when you write paper or report, the transparency aspect may lose. And the electricity rate from Energy Information Administration, EIA, they have monthly update. This link has a monthly updated information about statewide electricity rate, residential, commercial, industrial. And then there is this website, which I recently found very helpful, has a more detailed zip code wide electricity rates and time of use. So very close to our daily life, more accurate precision. Okay, Celeste, can you hear me? Okay, great.
Yes, yes.
Okay, I will continue. There is also PNNL's report on wastewater rates reported in 2023, which I found helpful. It has state level water rate, wastewater rate with some uncertainties bounded. And then transportation costs from American Transportation Research Institute, they update it annually, and the 2025 report is available in this link. So I would say TEA, LCA are more of a data battle. The more we can collect such data sources and have them handy, the more powerful we can down the road in conducting the analysis. So one example of testing which data sources we need to use for TEA. So Fisher Scientific and Sigma Aldrich, they are famous for supplying the lab scale high purity chemicals. So the quote I have for this sulfuric acid 500 milliliter is $160. Very expensive. And if you go to Chem Analyst for sulfuric acid in North America, oh, it doesn't have my updated screenshot, but this one is for North America pricing is $99 per metric ton per FOB free on board assessment. So the difference between these two sources is higher than 1,700. I still see papers in very high-end journals use this approach and conclude the technology is not profitable. We don't want to do that. We want to use more of a bulk pricing, purchasing pricing, rather than using retail lab scale cost data. And one company I talked to saying that it is quite a norm to discount the price from Fisher Scientific or Sigma Aldrich by 100 times to get some reasonable understanding of the bulk industrial cost. Okay, I probably need to speed up. And then based on the mass and energy amount, we just talked about how to convert it to cost. Now we talk about how to convert it to environmental impact. So first, we want to translate all the mass and energy flows into environmental flows. Environmental flows is an LCA term, which is essentially saying all the inputs from nature without prior human intervention, like water from rain, water from natural lake, and then outputs discarded to the environment without subsequent human transformation, like CO2 emitted to the air, some waste that we dumped into the land, for example, without any further human intervention. And then we can use some established databases to model these processes of translating mass and energy flow into elementary flows, such as EcoInvent and USLCI. Sometimes we don't have all the data available in the established databases. for our previous example of ADR, copper nitrate was not available in the database. Then we will model it ourselves. So in this screenshot, we have 1 kilogram of copper nitrate, and we model how much copper oxide was needed, how much water was needed, how much nitric acid was needed. And then, based on this tier of activity, we also want to track how nitric acid was made. So one more tier down here, how copper oxide was made. And then endless chain down below to track how the initial interaction with nature, maybe mining, happened, so that this tree will grow enormously. And we want to track the elementary flows in all these processes across the supply chain and add them up to estimate the impacts of our technology. The right-hand side table shows a small subset of those elementary flows shown as substances, such as water from turbine, some raw input from nature, the total amount. And then the databases based on addition of copper oxide, this flows, it will tell us for each product how much of each resources are needed. I redacted the information for the sake of complying with the end user license agreements of the software. Okay, and then once we collect the elementary flow, which is enormously long, thousands of data entries, we want to convert them into environmental impacts such as global warming. And we can use established methods such as TRACY, developed by US EPA, and RECIPE, developed by European institutions, and then sum the impacts of individual basin energy for the total estimate. And then we use LCA software to make the process easier. So it will be more of selecting the process in the software and click. And some representative software are CIMAPRO, OpenLCA, Gabi, Umberto, etc. The table here shows one example for the copper nitrate example. So we can convert the thousands of the substances or elementary flow from our modeling into 10 impact categories of the EPA's TRACY method, including global warming. And then we can see the impact of each input to this total impact. Again, this data is redacted for the license agreement. And then the next category is the equipment. We want to define what is the equipment requirement, such as name, industrial scale equipment name, size, temperature, pressure, etc. Quotes from vendors for the exact required equipment is always the best, but oftentimes not available, especially if the technology involves new equipment development. And then we could use databases or simulation software. Some examples are shown here, match.com, CapCost, CostMine, etc. Coming back to our earlier discussion of TRL, at the early TRL, we may use these databases, but as we define the technology to a higher level, we want to use more towards the vendor's quote. So the example table shown here is for the ADR technology using the match.com information and updated with some inflation rate. And we want to apply depreciation so that the cost of equipment, as it can be used for many years, will be appropriately allocated to different years. And then other costs, other capital, such as delivery of equipment, installation, instrumentation, piping. All these costs are essential for functioning of the equipment, but many times these are omitted in TEA. So we want to include this based on some factors. If the exact amount is not available at early TRL, as we don't actually purchase them, pipe them, and install them, in our facility, we can use some factors established. In this case, this Peter's book, Factors, was used. You can look into this Excel spreadsheet for this information more detail. So in essence, this will increase the capital investment from the initial purchase cost. This example is $8.8 million to $57 million. So about 8.5 times higher. And different references will use different factors, so these numbers may vary. Okay, and then lastly, the labor cost. Labor cost, a very good source is Bureau of Labor Statistics. It has very detailed information based on the location, job category, that is very useful. And then how do we estimate how many labor hours are required? There are several approaches available. This table shows one example that can calculate the amount of labors needed per unit per shift. So let's say for conveyor, we can use 0.2 operators per conveyor system per shift. The reference is from this book. And then other costs can also use factors at early TRL level, such as operating supervision. The previous slide talked about the direct operating labor. And then besides that, we want to have some supervision, some maintenance, supply, laboratory charges, which can be used based on established factors to estimate these costs at lower TRL. And don't forget about taxes, financing, interest, insurance, overhead, administration, etc. So this the same spreadsheet link can help us estimate these factors. And again, there are many different factors available from different references. Coming back to our ADR example, the original process flow diagram that we have evaluated is shown here. Use copper nitrate to produce rare earth oxide. And then preliminary TELCA showed the process is not economical, it's having high environmental impact compared to conventional process. And we look at what would be the improvement opportunities and found that there are two waste generation, and especially in here there is a lot of copper that is valuable resource that we can tap into to improve the technology. So copper recycling circuit was added by using some chemical approaches, and then wastewater from the second waste has been treated to be more compliant with the actual plant operation. And then the example result shown here saying that the process could cost $35 to $39 per kilogram of rare earth oxide output and revenue of $40 of $69 per kilogram rare earth oxide output, so that there could be some positive net profit margin. And there is some uncertainties around the feedstock composition, especially dispersion content and reaction efficiency. And the right-hand side figure shows the material cost breakdown. Because material cost is the major cost driver, we look into what material is causing the higher cost. And it's still, again, it's the copper salt nitrate, and then the processes of recycling the copper nitrate. And then we looked into the uncertainties of the product. As rare earth price fluctuate over time, we see that the potential revenue, if we apply the ADR technology over different years pricing of rare earth elements, we can see this bar chart are the revenue, and then this dashed line is the cost. So it could be profitable in the past 10 years of rare earth price, with profitability ranging from 2% to 81%. And then the environmental life cycle analysis, we compared the technology with the conventional rare earth mining from China. So the green chart shows the ADR technology, and then the rest 4 is the conventional benchmark Chinese production from mines. And because the recycled product produces unique product output, that are not directly translated available in the conventional market. Like conventionally, the closest we can find is 92% pure mixed rare earth oxide, as opposed to our product of 99.5% higher purity. And then this is the lower bound. The upper bound is 99.5% higher or higher pure individual rare earth oxide. So we looked into the impact of our product with this comparison and found that ADR could have lower environmental impact, especially if we can reuse the entire rare earth without separation. So the distinction between lower bound and upper bound is a major distinction is separation into individual processes, as rare earth in the swarf already contains the rare earth proportional for the NdFeB magnet application. By directly using them, it will be more sustainable compared to the conventional technology. And the right-hand side figure shows the contribution of each input and emissions on the ADR technology on the different environmental impact categories, saying that copper nitrate and copper nitrate recycling processes now reduced to have a relatively small impact compared to others. So through this example, we want to go back to our goal and check whether we have made that goals. The first one is quantify the potential economic environmental impacts. We did that. And then we want to identify what are the bottlenecks. Our bottlenecks were primarily copper salt. And then improvements was made on recycling the copper salt. And then we compared with the alternative conventional technologies to see what are the opportunities. And then we can inform decision making. In this case, we looked into the supply chain impact in this slide. Due to the time constraint, I'm not going through this slide. High level, it is saying that we can use the TALCA information to optimize the reverse logistics of recycling e-waste and recycling those swarf, so that we can minimize the logistic related costs and provide the maximum economically feasible solution. And then TE and LCA can help technology to mature from lower TRL to higher TRL. So the ADR technology was experimented from gram scale now to tons of scale, improved processes, and feedstock expanded to more dilute e-waste. And this slide shows the evolution of the technology from initial IP filing to partner with major companies to scale the technology. Okay, I will move on, and I want to acknowledge the support by Critical Materials Innovation Hub funded by US DOE, CMI, and MTO, as well as MTO for the reverse logistics supply chain analysis. These two figures show some of the students that I helped me along the process. They had with the major author for the ADR paper. And okay, if you have any question, please feel free to contact me. My information is available here. Thank you.
Awesome job, Hongyue. If anybody does have some questions, please feel free to add them to the chat. We have a few minutes here to address some questions. Hongyue, if you want to go back one slide, just so people can have your contact information there, that would be great. I have a question. I really appreciate you outlining different data sources and all the different data you need to collect for quality TEA and LCA analysis. What are maybe some common challenges that people might run into when they're trying to conduct one of these assessments, when trying to find valuable data sources or data sources that are accurate or reliable? What might be some tips or tricks that you might provide to people, or some common mistakes that you might want to avoid?
Yeah, that's a very good question. I think the data collection is the single largest challenge, and we want to estimate or collect the data that is most relevant for our analysis. I found that the search for literature and online sources for available information, such as the links that I mentioned. There are also other websites like University of Michigan, NLR, um, Argonne or NL. They have extensive databases also available from their website, and also talking with the industry partners, the potential suppliers of the equipment in the US, or sometimes we also talk with other international companies who are very helpful to help us to estimate more reasonable cost.
Makes sense. So looking for those valuable sources, those who are reliable sources, and going there first. Looks like we have a question in the chat.
Okay, let me read the question from Scott. Do you presume that reactions go to completion when running these simulations? Yes. Those Aspen, SuperPro, Sim, etc., mostly model some steady states. There are some variations that, like dynamic version of the Aspen, will look into the startup and phase out, but mostly on the steady state, and we give them the software some input on what would be the reaction efficiency. 95% based on experimental data or literature data, and what is the reasonable time. We provide the software this information, and if there are some errors, they will prevent us from running it, and then we go back and check what was the problem. Hopefully that answers your question, Scott. Okay, question from Will McClain. Can you comment a bit on the comparative LCAs, especially when comparing an emerging technology to conventional technology that exists in several different forms? For example, there may be older, inefficient technologies that drive up the average emissions of technology compared to the state-of-art conventional technology. The current typical versus SOA used by the DOE reports. Is there best practices here? Okay, so I think the question is saying there are some conventional technologies that are, some are more modernized, optimized, some are more using some inefficient technologies. So within those comparisons, there is variations that it is always best if you have that data in the comparative conventional technology using state of the art or some inefficient technology. I think those information is very helpful, and presenting them all and compare it with the current technology is helpful. Maybe the question is also pertaining to some efficiency improvement projected for the new technologies. There are some estimates like learning curve, what would be the efficiency improvement over time when we produce more and learn more about the technology that is feasible to apply. Not many people do that. So, and then if we are using developing some new materials, new ligand that is not commercially available, the current cost of production is very high. But how do we model as we improve production volume? It will decrease the cost based on optimization, scale up effect, etc. There are also some models that can help us to estimate those. Hopefully that answers your question, Will. Okay, Pen Cage. I'm sorry for my not good pronunciation. One question I have is, while going from lab scale to industrial scale economic modeling, how is the efficiency of different equipment considered? Will it be the same that we have in the lab scale, or is there any factors to that? The efficiency of different equipment considered when we come from in lab to industrial scale. So So we learn this as we go. The most technologies that I have worked with are lower TRL. As they advance TRL, they will be experimented with a higher processing volume and get new information about the efficiency. So one information I heard was that in the lab, they have stirring in 15 minutes will fully dissolve the rare earth, and as opposed to when we go into thousands of gallon scale, it required 2 hours to do that. And how do we estimate those efficiencies? I think it really depends. One helpful advice I heard is chemical engineering department. They have the reactor design courses that is relevant to this information. And then there are also some tools that will help us to estimate the impacts. For one of the cross-cutting research focus area upcoming meetings, we have meetings scheduled for estimating such an impact for pyrolysis. When we do pyrolysis in a small scale equipment, the time is very different than we model large scale equipment. And the teams develop some model in MATLAB and will present how to estimate that. Yeah, it will be different at different scales, and we want to collect at the larger scale possible information as possible, and then update the analysis according to different models. That is a very tricky question, a very important question. Question from Rachel. I really appreciated your emphasis on using ranges and bounds when assessing early scale technology. I have more of a communication-focused question. In your experience, how do you navigate the tension between stakeholders, waiting a single, simple answer, and the need to communicate uncertainty through the ranges and bounded estimates? Have you found effective ways to present that uncertainty without losing engagement or decision-making utility? Very good question. In LCA, there is relatively one pertinent question is we have 10 impact categories from Tracy, and how do we make it down to one single matrix so that we can present it to the final stakeholder and present one single solution? And there, the method is we typically convert it to like a recipe single score or something like that to make it easier to communicate. For uncertainties, I would say perhaps we can show percentages of MPV less than 0. So that is one number. Mean, that could be helpful, 95% range. Confidence interval, or maybe the Monte Carlo simulation range may be too much for this decision making, but yeah, that is a important aspect that I honestly didn't had encountered the problem much. I welcome some your sharing your experience on how to navigate this issue. Considering the time, I'm going to move forward. Alvin, I think generally the reaction simulation ends based on a user-defined endpoint, like when it reaches 95% or 99%. 100% reaction might take infinite time to simulate, I guess. We need to stop at some point. Okay, maybe it depends on the simulation software. For the software I'm most familiar with, the SuperPro Designer, we provide the efficiency. And to my knowledge, the software does not tend to go infinite time to recover the rest of the 5%. It is, we define it and then the simulation will run. Unless there is mass energy, some balance not provided to them correctly, they will run.
All right,
And then,
Hongyue, I'm gonna jump in really quickly just for the sake of
yes,
time. David, you are the last question, so I encourage you to please email Hongyue if you, or she can follow up with you if you're familiar. But for the sake of time, Hongyue, will you go to the last slide? Thank you all for all the great questions. This was a good conversation. Wanted to remind you that this webinar is recorded, and I apologize for those of you who might have had audio delays or audio issues earlier in the presentation. So please check it out on our YouTube channel. Maureen just dropped that into the chat for you to look at. This should be available in about a week. And we are taking a break in July with our monthly webinars, but we'll be back in August. So please keep an eye out on our socials and through our newsletters for our next webinar, which should be sometime in August. But thank you so much, Hongyue, for your presentation, and thank you so much for our audience for hanging with us. And please reach out to Hongyue with questions, and she's willing to share her slide deck with you so you can have some of those resources that she shared as well. Just please reach out to her. And with that, we'll end, and I hope you all have a great rest of your day. Thank you for attending.
thank you.